All right. So before we begin, let me start by asking just if there's any hiccups or administrative questions. The first homework is due a week from today, I guess, on Gradescope. So everyone know how to turn it in if need be. Everything's going well? Okay. Oh, yes. Why don't I come up with that this weekend, and then I will post it on Slack. It will be roughly midterm. That's what I'm gonna aim for. Just need to figure out the exact date. But let me commit to doing that over the weekend, and remind me if I don't. Good. Other questions? Okay. So just sort of maybe briefly recapping where we are in the story of this course and motivating what I want to do today. Okay, so we sort of, we gave all of the classical definitions of game theory, best response is equilibria, caused everyone who took Econ 101 or game theory 101 in the econ department to remember it. And we sort of said, well, in this class, we're not so interested necessarily in sort of 2x2 games. We're interested in making predictions in large games. And we said sort of in order to do that, we need to think of, number one, structured classes of games, right? Classes of games that at least conceivably someone could fit in their minds. Even unstructured games are sort of exponentially large in the number of players. And that although this classical idea from game theory and economics that we shouldn't expect to see, if gameplay is going to stabilize anywhere, it will have to be at a stable state of the game. That's sort of tautological, but concretely that says if we're going to predict, if anything's going to be predictable at all, if it's not going to be some sort of chaotic system, forever changing, if it's going to stabilize anywhere, it will be at some notion of equilibrium where everyone is best responding to everyone else, roughly speaking, because otherwise it wouldn't be stable. But we sort of said, okay, that's fine. If there is going to be a stable state, it'll probably be an equilibrium of some sort. But even when equilibria exist, why should they be plausible predictions? We sort of want a computationally plausible story, not just for why you stay there if you ever reach an equilibrium, but for how you get there. Okay, and what we did last class is we sort of gave, if you like, sort of a first case study in when this might be, right? We defined a reasonably expressive class of games, class of large games, congestion games that had concise descriptions. We studied a reasonably natural dynamic, best response dynamics, that was pretty general. There was a lot of unspecified moving parts, unspecified in a good way, meaning it didn't matter what the starting state was. It didn't matter the order in which people took turns improving their action. It didn't matter exactly how they improved their action. They didn't have to play an exact best response, just a better response, right? And we sort of showed, okay, if you sort of believe that what people might do is roughly described by some instantiation of this better response dynamics that we studied, then you should sort of believe that Nash equilibria, in particular pure strategy Nash equilibria, are reasonable predictions in the context of congestion games because this dynamic sort of inevitably leads to them, and in fact quickly leads to at least approximate Nash equilibrium. Okay, so that's what we did last time. And what I want to do this time is sort of ask how far, if we think of best response dynamics as one computationally plausible story for how people might end up at equilibrium, I want to ask, how far can we push that story? How broadly, how much explanatory power does best response dynamics have for sort of play converging to Nash equilibria beyond congestion games? Like, is what we proved last class it? Like, is best response dynamics sort of a dynamic that really only makes sense to think about in congestion games? Or are there things that are not congestion games for which best response dynamics converges? Does it converge? We already know it doesn't converge in every game. Like in particular, there are games for which there are no pure strategy Nash equilibria, like rock, paper, scissors. And as we saw last time, if we can prove the best response dynamics converges, well, that's a proof that the game in question has a pure strategy Nash equilibria. So, like we know for sure the class of games that it converges in can't be all games. But the question is, can we characterize exactly the class of games for which best response dynamics converges, and sort of, say we sort of fully understand this part of the story, right? If you are a game in this class, best response dynamics converges. If you're not, it doesn't. Okay, so that's the plan for today. And like concretely, the way I want to get there is I want to consider a couple of more sort of case studies. I want to study two games, neither of which are congestion games. Okay, they're related to things we've studied. And in each of those games, I want to prove that best response dynamics converges, despite the fact that they're not congestion games. Okay, so like, like answering the first part of that question, these first two examples will show us that congestion games are not it. Like there's stuff that is not, there are games that are not congestion games for which best response dynamics converges. And in doing that, we're gonna go through a couple more examples of this style of proof we saw last time that sort of tracks a potential function in service of arguing that best response dynamics converges in these games. And having seen, three proofs in this style, the one from last class for congestion games and the two today, what I then want to do is sort of try to abstract away what structure specifically we needed those games to have in order for the proof to go through, and to use that structure to characterize exactly when best response dynamics converges. I want to give an if and only if characterization that says, if your game has this property, best response dynamics converges. If not, it doesn't. Okay, so that's the plan for today. Are there any questions either about the general narrative we're building up here, details of what we did last time, or questions about what I assert we're going to do today? Yeah.
So before everything, all the updates were done sequentially, one by one.
Yes, best response dynamics is a sequential dynamic.
Would everything still work if updates are made simultaneously?
What do you think?
No.
No. How come?
Might run into like some kind of cycle.
Yeah, like you can. So the question was, best response dynamics is like a sequential dynamic. If we said everyone updated simultaneously, would the theorem we proved last class still be true? The answer is no. You can sort of like imagine why it is, even just in like a simple traffic routing game. Right, so suppose you've got a traffic routing game, super simple. It's like, two roads up and down. And the delay is just the number of people that take the road. So the equilibrium is like half the people take the top road, half the people take the bottom road. And so, okay, suppose we start out with everyone taking the top road. You can sort of see how sequential best response dynamics is inevitably gonna very directly converge to equilibrium, just one by one. While there are more people on the top road than the bottom road, people will switch from the top road to the bottom road until it's an even split, and then we'll be done. But like if you think about simultaneous best response dynamics, suppose everyone's like moving along the top road, and everyone simultaneously looks and they says, it's like 100 people on this top road, there's 0 people on this bottom road. Tomorrow I'm going to switch to the bottom road, and okay, so they do that. And then there's 100 people on this bottom road and nobody on the top road, and it'll just cycle back and forth. So there's some kind of like symmetry that hasn't been broken there if we literally look at sequential best response dynamics. Or simultaneous best response dynamics, right? So you can think of, right? So you can think of sequential best response dynamics as just some kind of, if you like, perturbation of simultaneous best response dynamics. Like, maybe not everyone changes their action at literally the same time, even if there's just sort of like random offsets that induces some ordering in which people make their decisions. And we don't care what the ordering is. The analysis we went through doesn't care what the ordering is, but like it does have to not be simultaneous to avoid this kind of cycle. Good question. Yes.
For those response dynamics, does players changing their action have to change it to the one with the biggest increase in utility?
Any increase in utility was good enough for our analysis. Yeah, so that was sort of a strength, a generality that was sort of nice. Like, right, we're also trying to tell a story here in which we are assuming only sort of, making minimal assumptions about the players. They don't need to be able to exactly optimize their path. They just need to be able to do something that improves on what they're currently doing. Good question. Other questions? Okay. So let me start by telling you about a game that is not quite a congestion game, although it will look a lot like a congestion game. After I tell you what the game is, I'm going to ask you to tell me why it's not a congestion game. You can try to remember the specifics of what defined a congestion game. Okay, but here's the game we're talking about. It's going to look a lot like a congestion game. And it's called a load balancing game on identical machines. So think about this as modeling something like the following. There's a bunch of servers. Those are sort of like the facilities. And there's a bunch of players who correspond to people who would like to schedule one job, like one run of their piece of code on one of these machines. Okay, and the machines are identical. So it's not like one has a better GPU than the other, but the other one has more RAM or something. We'll think about on the homework the case when that is the case, when the machines are not identical. But here the machines are identical, so the players don't have any a priori preference over what machine their job runs on. But the jobs have different sizes, right? Like you might be running like linear regression. I might be training, ResNet 50 to classify ImageNet. Mine's going to take longer to run than yours. And the way that is represented is each of the players who correspond to people who want to run single jobs has a size or a weight that I'll call WI. Okay, so intuitively, the bigger my job is, the longer it's going to take to run, the bigger my WI. Okay, so that's just like a characteristic that's inherent to the players. They each have some fixed job of some fixed size they'd like to run. And the action space is just the set of machines, the set of facilities. So I can choose a machine to schedule my job on. Okay, so there's 10 machines. My action space is just 1 through 10. I point to one of the machines, that's where I'm going to send my job. Now the way jobs are processed on these machines is not like first come, first serve or anything like that. It's like some kind of round robin scheduling. And so all of the jobs on a particular machine are going to finish at the same time. Okay, so it's not that some of them are going to finish earlier than others. They're all going to finish at the same time. And well, what is that time? Well, we need to wait until we can, we've had enough computation time to run all of the jobs on that machine. So the load on that machine, right, the cumulative running time for all of the jobs scheduled on that machine is just the sum over all of the players who decided to schedule their job on that machine, machine J, of the weight of that player. Okay, so there's some number of jobs assigned to machine 2. Those jobs have some weight, like maybe the first one has weight 6 and the next one has weight 3, and there's another one that has weight 1. The load on that machine is 10. Okay, and the cost of a player is like the amount of time he needs to wait before his job completes. It's just the load on the machine he chose. Okay, so it looks kind of like a congestion game, right? Like there's players, there's facilities, those are the machines. The action space of each player corresponds to a subset of the facilities. In this case, a very simple subset, just a singleton. You just pick one of the facilities. And the load on a facility, which is equal to the cost of the player who chooses that facility, is just the sum of the weights of the players who chose that facility. Yeah. That's sort of motivating why the cost of a player is equal to the load of the machine he chose. Because like if I ran the small jobs before the big ones, you might, if you were a small job, you might not care that there were big jobs running after you. But just to have a simple model like this, where the cost of a player is equal to the load of the machine, no matter, right? There's no aspect of time here where some of the jobs finish earlier. Yeah, like I asked you to imagine a world where the jobs all finish at the same time. Okay, is the game clear? People have weights. They point to machines. The load on a machine is the sum of the weights of the people who pointed to it. And the cost of a player is equal to the weight of the machine she pointed to. Yeah. One machine, yeah, you can't like split your job across multiple machines, you just run it on one machine. Okay. Nevertheless, I claim this is not a congestion game, as we defined it last time, and so our proof from last time does not like imply that best response dynamics must converge in this game. Can anyone tell me why this is not a congestion game? Yeah. That's right. So in a congestion game, the way we defined it, the cost of a facility was a function only of the number of players using that facility, but in particular, not the identity of those players. We didn't care who was driving on the same road as us, just the number of people who were driving on the same road. And so if all of the jobs were identical, if all of the jobs had weight 1, for example, and all I cared about was therefore the number of people who were running jobs on my machine, this would be a congestion game. But because they're not, and the load of a machine cannot be expressed just as a function of the number of people playing on that machine, but actually, cares about who they are because it's the sum of their weights, this is not a congestion game. Okay, is that clear? Yeah.
You see that like a congestion game is like a special case of this, but all the weights are equal to 1.
I think you can rearrange those words into a correct sentence. So if all the weights are 1, this is a special case of a congestion game. Right, like this would be a congestion game if all of the weights were identical. Okay. But a congestion game, right, like the class of congestion games, of course, in some aspects is much more general than this, in that, like the action set can be in general like a subset of the facilities, right? So like this doesn't capture road networks. So congestion games, this is not a generalization of congestion games, but neither is it a congestion game because of the weights. Yeah, not being 1. You could, by the way, you could define a generalization of congestion games, like weighted congestion games, where the action space is arbitrary subsets of the facilities once more, but now the cost of each facility is the sum of like the weights of the players on it. And I think on one of the upcoming homeworks, you will show that in fact, best response dynamics need not converge in weighted congestion games. So although you could define that generalization of congestion games, like it wouldn't be true that best response dynamics converges in that class of games. But like nevertheless, we're going to show in this particular game it does. Does that make sense?
Yeah.
Okay, good. Other questions about either the specifics of what this game are or why it is not a congestion game, why our proof from last time doesn't apply? right? Like if you remember, our potential function last time sort of made crucial use of like the fact that the cost of each facility depends only on the number of people using it, right? Like it's summed from the number of people, a number of people ranging from 1 to, like the number of people actually on the facility of the cost of the facility when that many people were on it. So like, it's not just like a technicality that this isn't a congestion game, but like exactly the same proof applies. Like our proof from last time actually used the fact that is not true in this game, that the load on a facility depended only on the number of people playing on it. Okay. Okay. Nevertheless, I claim that best response dynamics converges in load balancing games on identical machines. Okay, so if you can run best response dynamics on this class of games, or imagine it being run, and you'll come to the same conclusion, even though this is not a congestion game. It converges to Nash equilibrium. And like in particular, like load balancing games on identical machines must therefore have pure strategy Nash equilibrium. Okay, and I'm going to sort of go through this proof, and in many respects, it's going to be quite similar to the proof that best response dynamics converges in congestion games. We'll have to use a different potential function. But like, there will be a minor difference in how we derive the conclusion that I sort of want to focus on, because remember, our goal from seeing this example on the next one is to try to like focus on the aspects of the proof that are sort of important and those that aren't, and try to abstract away from the important ones exactly the class of games for which best response dynamics converges. Okay. So at a high level, the form of the proof is going to be quite similar, right? Like, and just to sort of remember, like, the main thing we need to deal with, as players take turns making better responses in a game, like basically the only thing we know directly from the definition of a better response is that at the moment at which they change their action, they take their better response, their cost decreases. Like that's what it means that it's a better response. And so it's like tempting to just try to like say, okay, well, like, they're decreasing their costs and that can't happen forever, so play converges. But like, that's not right, because my cost decreases at the moment that I change my action. But then it's your turn, and your cost decreases at the moment that you change your action, but your change in action might have increased my cost. And so this doesn't rule out cycles. And that's why we need to identify something else, some other single function, this thing called a potential function that is sort of like accumulating the progress. And right, it's important to have this one single function that is decreasing at every round of best response dynamics, so that we can have some way of measuring quantifiable progress, right? Like that's the engine of the proof. And so, yeah, and so what we want to do, once again, at a high level, is identify some potential function and argue, because we know that each individual player's cost decreases at the moment at which they change their action, that the potential function must decrease. We need to connect somehow the change in potential to the change in an individual player's cost. That's and so it's the same high level strategy as last time. Okay. So we've got to use a different potential function this time. And the potential function is going to be the sum of the squares of the load on each of the machines. Okay, maybe half of that just for convenience, but the half is not really important. Okay, and probably right to whenever I like whip a potential function out of my hat, the question is, where did it come from? Okay, so in some sense, the potential function, of course, is reverse engineered to make what will follow work out, right? You sort of know the pattern of what has to work out, and you want to find a potential function that has that property. But maybe sort of intuitively, what are you encouraging when you're asking for like the sum of the squares of a bunch of numbers to be small. You're sort of encouraging that the weight be as evenly as possible partitioned across the machines, because the marginal contribution of like a unit of weight on a large machine is more than it is on a small machine if we're squaring the weights. Okay, and sort of intuitively, like at equilibrium, you know, like the weights should be sort of evenly distributed, because there should be no way for someone to move from a more loaded machine to a less loaded machine that like decreases their cost. So that's sort of, you know, that's why you might, when you're hunting for a potential function in a game like this, consider something like squares of losses. Okay, now remember, the thing we know in better response dynamics is that individual players decrease their cost when they change their action. Okay, so we want to understand what an individual player's change in cost looks like and relate that to the potential function somehow. Right, so just like we did for congestion games, let's think about what happens when a particular player I switches from some machine J to some other machine J prime. Right, what's their change in cost? Well, like definitionally, it's the load, it's their cost after they switch. So the load on machine J prime after they switch to it, we'll have to take into account the fact that their weight is now on it, minus their cost before they switched, which was the load on machine J, right, their load before they switched. Okay, so after they switch, they have to pay for the load of the machine they're on, but the load of the machine they're on has increased because now they're on it as well. Okay, so after they switch, their cost is the load of machine J prime, adduction profile A, that was like what it was before they switched, plus their own weight, plus WI, because they add to the weight of the machine. And before they switched, it was just the load of machine J, which adduction profile A already included their own weight. And we know, like if nothing else, right, the one thing we know about better response dynamics is that like this expression has got to be negative, because the fact that they made the switch, right, means that this switch was a good idea for them to make. They decrease their cost. Okay, so like this is like the one fact we have to work with, that this expression here, the load of machine J prime plus WI, their cost after they switched, minus the load of machine J, that is negative. And we need to argue based on that fact that the potential function is decreasing. Okay, so now I want to think about what the change in potential looks like when the same switch happens, when player I switches from machine J to machine J prime. And I want to relate it to this expression somehow. So I want to look at the difference between the potential after the switch, when player I is playing J prime, to the potential before the switch, when player I is playing J. And we can just write out what this is, right? Like, so nothing's going on here other than unraveling the definition of the potential function, which is the sum of the squares of the machines. So like, first of all, like for any machine that's not either J or J prime, right, the one that player I switched to and from, the load has not changed, right? Nothing has changed for those other machines. So when we're looking at the difference in potential, the difference, like the only terms that won't cancel out are the terms corresponding to machine J and machine J prime. Those are the only machines whose load has changed. Everything else cancels out in this difference. Okay, so this difference is really just the squared load of the machines after the switch minus the squared load of the machines before the switch, right? And the only machines that have changed are J and J prime. So after the switch, what's the load of machine J prime squared? Well, it's just the load of machine J prime before the switch plus the weight of player I, WI, squared. And similarly, the load of machine J after the switch is the load of machine J before the switch minus WI squared, right? Because this weight Wi shifted from machine J to machine J prime. Okay, and before the switch, well, like the shift hadn't happened yet. So it's just the load of machine J prime squared minus the load of machine J squared. So this is just, like literally looked up at the definition of the potential function and written down like, syntactically what the change was. Is that clear? But now, like, we're going to see some cancellation of terms, right? Because we've got, like a square here. So what's, a plus b squared? It's like a squared plus 2ab plus b squared, right? So we're going to get like a, load of machine j prime squared term and a load of machine j squared term. And those are going to immediately cancel out with their negative counterparts. And so what we're going to be left with is just the cross terms, right? So what are the cross terms? We have, 2 times the weight of player I times the load of machine J prime plus the weight of player I squared. Okay, that's the first cross term, first pair of cross terms. The second pair of cross terms are, 2 times the load of machine J times the negative of the weight of player I, plus, again, player I's weight squared. And all of the other terms, the load of machine J and J prime squared have canceled out. Okay, so this is just expanding out the quadratic and canceling terms. And remember, like, what is our goal? Our goal is to somehow relate this to this. So we'd like to do some algebra to find this expression within here. So let's do that. Let's simplify. So like, first of all, there's this convenient factor of 1/2 out here that'll just get rid of these 2's. And so what are we left with? Well, like, we can notice that every term inside here includes a factor of Wi, the weight of player I. So we can pull that out. And we can observe that this is just like the weight of player I times the load of machine J prime plus Wi minus the load of machine J. Okay. And so we've done it. We've found this term up here, the change in player I's cost, somehow inside this expression for the change in the potential. Right, so this is just Wi times the change in player I's cost. And since we know the change in player I's cost was negative, we also know the change in potential was negative. Okay, and so because the potential function must strictly decrease with every better response move and can't go below 0. And it's only a finite number of game states. This means we have to converge to best response dynamics. Otherwise, we would repeat a game state, which would contradict this strictly decreasing property. Okay, so we're done. And what I want to highlight here is that when we went through this sort of similar proof for congestion games, what we did is we said, okay, well, the change in potential was exactly equal to the change in player I's cost, right? Like, that was how the potential function was rigged up. But like, the small thing I want to notice here is we didn't need that. That's not true here, right? Like, the change in potential is not equal to the change in player I's cost. In fact, because this is a weighted congestion game, you wouldn't be able to find a potential function that has that property. But that's okay. We didn't need it. We only needed the fact that like, we didn't need these numbers to be the same. We needed them to have the same sign, right? We needed that we could figure out from the fact that player I's cost decreased after his better response move, that the potential also decreased. We didn't need the magnitude of the decrease to be the same. Okay. And so we've proved the theorem, best response dynamics converges in these weighted load balancing games. Questions about that? Yeah. This one? this is just, so what is the potential function? It's the sum of the squares of the loads of the machines. Okay, so we've got the sum of the squares of all of the loads of the machines here. And we're subtracting off from that the sum of the squares of all of the loads of the machines before player I made his move. Now player I moved from J to J prime. So the load on machine J changed, the load on machine J prime changed, but the load on all of the other machines did not change. So when we're looking at this difference, like the loads for any machine whose name is not J or J prime, those just cancel out in the difference because they're the same. And so this is just the load out of machine J after the switch squared, plus the load of machine J prime after the switch squared, minus their loads before the switch. Does that make sense? Good. Other questions? Okay. All right, so the proof works even if the change in potential is not the change in cost. And as like a fun fact, it's possible to rig up a potential function in which the change in cost is equal to the change in potential, like only if it's a congestion game, but you don't need that for the proof to work. Okay. So that like wasn't a congestion game, but it kind of looked like a congestion game, right? There were like facilities and people were playing on them, and they had their, like their actions were subsets of the facilities, and their costs were equal to the cost of the facility. So although the proof was like a tiny bit different, you might think to yourself, like maybe fine, it's not just congestion games on which best response dynamics converges, but it's like, things that are basically congestion games. And so I want to just go through like one more example of a game in which best response dynamics converges, like a super simple game that just doesn't look like a congestion game, like doesn't have facilities, for example. Okay, and I'll call this the red state, blue state game, but it's, really simple game, but maybe is supposed to model some kind of polarization phenomena. And so the idea is, underlying this game is a graph, which maybe you can think of, if it's helpful, as sort of like a social network graph. The vertices are the players, and the edges correspond to some kind of affinity, like friendship. Okay, and in fact, it could be a weighted graph. So like the weights could correspond to like, the degree of friendship. They could even be negative weights, so you could have enemies recorded in this graph. And the players are the vertices. Okay, and the players need to pick between one of two options. Okay, so you can think of them as, political positions. That's probably like what the name of the game is trying to get you to think of. But like, really, it could be sort of any two options in which there are any kind of network effects. So you could think of it as getting a Mac or a PC or an Android phone or an iPhone, joining Twitter or Mastodon or whatever. Okay. And the point is, in this game, you don't have any a priori preference for which of these two options that you pick, red or blue, but you'd really like to pick, like there's some kind of like network effects here. Like you'd really like to have picked the same option that your friends picked, and maybe a different option than your enemies picked. Okay, so what's your utility? Well, and just like notationally to make it easy to write out the utility functions, let's identify the two options as 1 or -1. Okay, so you're picking 1 or -1. And the reason why that'll just be like convenient notationally is because if I multiply my choice by your choice, it'll be 1 if we picked the same thing, and it'll be -1 if we picked something different. Okay, so what's my utility? Well, it's the sum over all of my neighbors in the graph, all of the people that I'm connected to in this social network, of the weight of our connection, the weight of the edge connecting me to you, times my choice times your choice. And remember, my choice times your choice is 1 if we pick the same thing, and it's -1 if we pick something different. So this is the same thing as the sum of the weights I have to everybody in this network who picked the same choice as me, minus the sum of the weights of everybody I'm connected to in this network for people who picked a different choice than me. So I get like positive utility when my friends have the same affiliation as I do, and I get negative utility when my friends have an opposite affiliation to me. Okay, yeah. The weights can be negative. Yeah, so if you want to have enemies in here with negative weights, for the enemies, you would get, negative utility if they pick this. It's embarrassing to, have the same political beliefs as your, dumbest enemies, and you're proud to have picked the opposite from them. So yes, we won't require in the analysis that the weights are positive. Yeah.
So are we meant to graph or at least produce that point?
Yeah, I mean, like, I guess, like, since we have weights, like, without loss of generality, it could be a complete graph. And if you wanted to model an edge not existing, you just give it weight 0. But it doesn't have to be a complete graph. Basically, the lack of an edge is equivalent to having an edge of weight 0 in this model. Good question. Other questions about the game? Okay, so like, not really a congestion game. Like, it's hard to think about how you'd map this onto something that looks like a congestion game. Like if you tried to say, well, 1 and -1 are facilities or something, the problem is not just now that there are weights, of course, like, so you care who picks your affiliation and like what their weights are, but you also care who picks the other affiliation. Okay, so just it's some game, not a congestion game. Okay. Nevertheless, the claim is that, I'll state it, the reverse set of implications. Like, people don't have to randomize here to come to a stable state. This game always has pure strategy Nash equilibria, always has a pure strategy Nash equilibrium. And in fact, the way we are going to establish this is we're going to argue that best response dynamics converges. Right, so like, really the theorem is best response dynamics converges in the red state, blue state game. But like, in particular, this proves it's got a pure strategy Nash equilibria, which again, isn't like a priori obvious. And so let's go through this proof one more time. This will be like the 3rd time we've seen a proof in this style. And once again, like, we basically need to find the right potential function. Here it is. Now, when you need to find one of these, like on a homework problem, you should really approach this in the reverse direction. Like, when I present this on a slide, the potential function is the first thing, and then I calculate like the change in player-ized cost and the change in potential, and like, lo and behold, I chose the right potential function. But like, you, in trying to come up with the potential function, should probably be working your way backwards up this slide. Like, calculate the change in player-ized cost, calculate the change in potential, and try to figure out what would be the potential function you could choose that would allow you to relate them. But okay, here's our potential function. What do I mean notationally by the sum of, j less than I? I mean, I don't want to double count edges. So I'm going to sum up over all pairs, all of the edges, all pairs I and j, but so that I don't count the edge twice, once from I to j and once from j to I, I'm only going to count the pairs in the order in which j is less than I. But this just means I'm summing up over all of the edges in the graph, and I'm counting each one once. Okay, so what's the potential function? It's the sum over all of the edges in the graph, not double counting, of the weight of that edge, the weight of the edge between I and j, times the choice of action I times the choice of action j. So sorry, the choice of player I times the choice of player J, which remember is just 1 if they're the same and -1 if they're not. So it's the sum of all of the edges in the graph of plus the weight of that edge if player I and J pick the same action, and minus the weight of the edge if they picked a different action. Okay, that's the potential function. And once again, turning the crank on our proof template, we want to think about what is the change in a particular player I's cost when they change their action. The reason we want to think about that is because that is really the only object that we have any handle on. We know that the change in cost of a player will be some monotone quantity because players change their action only when it decreases their cost or increases their utility. Okay, so what is it in this case? Well, first of all, what does changing your action even mean in this game? There's only 2 actions, 1 and -1. And so changing your action is like the same thing as multiplying your action by -1, right? Like either you're going to switch from affiliation 1 to affiliation -1, or you'll switch from affiliation -1 to affiliation 1. This is another place where we're sort of getting something out of our convenient convention of associating the 2 actions with 1 and -1. Changing your action corresponds to multiplying by -1. Okay, so before your change, your utility was the sum over all of your neighbors in the graph of the weight of the edge between you and your neighbor times your choice times your neighbor's choice. And after your change, it was the same thing, except your choice now changed from whatever it was before, AI, to minus that, minus AI. Okay. And so this is an especially simple expression, your change in utility. Well, right, like, it's your utility before minus negative your utility before. So it's just twice your utility before the change, right? Your change in utility is always exactly equal to twice your utility before the change. Does that make sense? Okay. Now the next step in this proof template is to make sure that to look at the change in potential and make sure that we're making progress along this one single axis we've defined. And the only tool we have to do that is to try to find somehow within the expression for change in potential, like the expression for change in player I's utility, because we know the sign of that thing at least. And so we do what we need to do. We write out the change in potential, which in this case, right, like what's the potential function before the change? Well, it's just the sum over all of the edges, counting each one exactly once, of the weight of the edge times the choice of the left endpoint times the choice of the right endpoint. And in particular, like player I is the one who's changed his action. And so any edge that did not involve player I cancels out in this difference in potential, right? Like, any term that did not involve player I is the same before and afterwards. So the only terms here that change, this is a confusing notation, because I here is a constant. I is the name of the particular player who changed his action. The index of summation here is only J, right? The only terms that change are those terms corresponding to edges that had one endpoint at player I. Right, so the changed terms are the edges that had one endpoint at player I, the other endpoint was somewhere else, J. And so the change in potential, it's the sum over all of those edges, all of those Ji pairs of the weight of the edge times Ai times Aj. That was what it was before the change. And then after the change, we sum over the same set of edges, but Ai now negated his action. And so the change in potential is exactly equal to the change in player I's utility. And so we know that player I is always moving such that his utility increases after his move. The potential also moves monotonically, and therefore we can rule out cycles and establish that best response dynamics converges and that these red state, blue state games have pure strategy Nash equilibrium. Okay. Yeah.
Like an example of a social welfare.
Let's see. So if we summed over the utility of all of the players, I guess we would count each edge twice. But I guess this is half of social welfare. So yeah, this is an example of a game where it happens that social welfare is a potential function, and every better response move not only improves the utility of that player, but improves social welfare, which is something that wasn't true in the last two games we studied. So yes, good point. Yes.
So AI switches to like the new action.
AI is the old action. So this is like the potential at state A, and then we're considering what happens when player I changes his action, which just corresponds to like negating. So like negative AI is the new action.
So when we calculate the change, I thought we do final minus the like we start with what like the end of the final change.
Yeah, as long as you do it consistently in the change in utility and the change in potential, it doesn't really matter. Right, like, so I guess, here the utility after the change will be higher because people are maximizing utility instead of minimizing cost. And so we've written things in this way so that the change is like negative as it was in the previous games. In the previous games, it was cost instead of utility. But if we had written things the other way around, it would have been fine so long as we hadn't like used different orderings in our different calculations. We just want that directionally the change in utility or cost is the same as the change in potential. It doesn't really matter if, right, maybe that's a useful thing to point out, right? Like, so like, we noticed in the last proof that we sort of don't care that the change in utility is exactly equal to the change in cost. Like, we only care that the signs are the same. We've also sort of been talking about decreasing potential functions, but like an increasing potential function would be just as good, right? We just need to, the meat of the proof is sort of ruling out the possibility that there are cycles, that we ever visit the same state twice. So as long as the potential function is making monotonic progress, either upwards or downwards, we're okay. Does that make sense? Okay. Okay, so now we've seen, 3 examples of this proof, basically. I want to think like, okay, what do we need? What property does a game need to like make this proof work? And so, it seems very closely related to potential functions. So why don't we give a name to the kinds of things we're talking about? So a function that maps game states to numbers, we'll call it an exact potential function for a game if for every game state and for every player who might change his action, and for every action bi that he might change his action to, we have that the change in the potential function after the switch compared to before the switch is exactly equal to the change in player i's costs after the switch compared to before the switch. Okay, so for congestion games and for the red state, blue state game, we gave exact potential functions. Those were functions that had this property, that we could relate for every game state, for every player, and for every deviation in that player, exactly her change in cost with the change in potential. But we saw this example of the load balancing game, the weighted load balancing game, that we proved best response dynamics converged without an exact potential function. And so I guess we don't really need an exact potential function for this proof to work out. We really only need an ordinal potential function. What is an ordinal potential function? Well, again, it's like some object that just sort of labels game states with numbers, right? It's like you've got a label gun, and so it's a way of writing a number on every game state. And it should have the property that for every game state and every player I and every deviation, every change in action that player I might consider, changing his action from AI to some other action BI, that if the change in action decreases player I's cost, then the change in action also decreases the potential function. Right, that's really, this was sort of what we needed to make the proof go through, because the fact that we were playing best response dynamics gave us the left side of this implication, that player I's cost decreased through this move. And we used the right side of the implication, that the potential function decreased. Right, so an ordinal potential function is more general than an exact potential function. Exact potential functions, of course, are ordinal potential functions, but the reverse is not necessarily true. In particular, like the potential function we used in the load balancing game was not an exact potential function. Okay. So is it clear what an ordinal potential function is and why, at least if we want to use the same proof template we've been using to prove that best response dynamics converges, it is sufficient if someone shows us an ordinal potential function? Right, because again, like the way the proof works is, we need to argue that at every step the potential decreases, because that tells us we can never return to the same state twice. And the thing best response tells us is that every time a player takes a move in the dynamic, it's because their cost has decreased. And this is exactly the implication we need to get the conclusion that, when someone takes a move, the potential decreases. Okay. So like hopefully, you've seen the proof 3 times now. You could write out a general proof that sort of says, if I give you an ordinal potential function, if a game has an ordinal potential function, then best response dynamics converges. Okay. But like you might at this point wonder, like, okay, like we've been hammering at this like one like proof technology, like find a potential function and like squeeze it until you get convergence of best response dynamics, and like if you like squeeze hard, you realize, okay, like an ordinal potential function is sufficient. But you might think, okay, but like maybe there's only so much you can get from like squeezing this one proof technology. Like maybe this is just not a powerful enough argument to argue that best response dynamics converges in all games. Like maybe there are games that don't have ordinal potential functions, but nevertheless such that best response dynamics converges, right? Like that's a completely reasonable thing to believe. Like in general, like, the same proof technique doesn't work for, all categories of statements you might want to prove. Right, so you might think, okay, fine, like, this somehow maybe characterizes like the class of games you can prove, you can prove in which best response dynamics converges using this particular proof technique, but like that's not an interesting class because maybe there are games that for which best response dynamics converges, but like to prove it, you need some entirely different technique. Right, that's a reasonable thing to believe. But it's not true. This is a sort of complete proof technique for best response dynamics. Right, so this is going to give us a characterization of exactly when best response dynamics converges. So the claim is that best response dynamics is guaranteed to converge in a game G if and only if the game has an ordinal potential function. Okay, so like hopefully now you can sort of recite off by rote the proof that if a game has an ordinal potential function, then best response dynamics converges in that game. But I claim the reverse is also true. If best response dynamics converges in the game, it has an ordinal potential function. And so, like the complaint that I have, you might have considered like complaining that I've like crippled your career proving that best response dynamics converges in different classes of games by only teaching you one method of proof. But I can respond and say it's the only one you need. Like, if best response dynamics converges, you might as well try to do it by just keep continuing to look for that ordinal potential. Yeah.
I guess that was my question. Right? Even if we do prove this, you can tell the game has
Oh no, not necessarily. I mean, it's exactly as difficult to tell as it is to tell that best response dynamics converges. But if best response dynamics converges, there is an ordinal potential function. But yeah, it still might require like cleverness. It's not like this mechanizes like, it's not like there's a decision. It's not like there's an algorithm that can take as input a description of a game and mechanistically tell you does best response dynamics converge or not. Although, as we'll see when we prove this, there is sort of a mechanistic way to think about it but it might not be computationally efficient. Yeah, so this doesn't mean that like your next problem set's easy. It just means, there's always a proof of this form. Good question. So other questions before we like jump in and prove this? Other questions about like what the theorem is saying?
Best response dynamics is that just that each iteration of play.
Yeah, good question. So like, what do I mean by best response dynamics? I mean basically something like, I mean every instantiation of the algorithm we've been proving things with so far. So it means, yeah, like at every iteration, someone chooses an action that is a better response. But like, I also want it to hold for every starting point and for every sequence, for every ordering in which people might pick best responses. So you might mean something more limited, that there exists a starting point and there exists a particular special sequence of rounds in which people can play, better responses that converges to equilibrium. But I claim that wouldn't, if I replaced all these universal quantifiers, for all with existential ones, there exists, that wouldn't be very interesting. Because of course, if I start at a Nash equilibrium, then okay, best response dynamics won't leave it. So when I say best response dynamics, I really mean, when I say best response dynamics converges, I mean it's got to be that no matter where I start from, and no matter what order in which I let people change their actions to decrease their cost, we must, there's no way to get in a cycle. You must converge to Nash equilibrium. Good point. Other questions about what the theorem says before we prove it? Okay. So, okay, we've done, again, like the forward direction. If there's an ordinal potential function, then best response dynamics converges. We've basically seen that proof 3 times. So I'm not gonna do it again, but like you should introspect and make sure you remember how to do that. Let's prove the opposite direction. So I wanna think, I'm starting from the statement that best response dynamics converges in some class of games. And what I need to do in the proof is I need to like think about that statement and somehow extract from it an ordinal potential function that I can demonstrate to you. Okay, so the nature of the input-output behavior of the proof is you give me a game in which best response dynamics converges. I somehow process that game into an ordinal potential function. Okay, so I want to think about a graph, sort of an abstract graph that is described here, but maybe let me like tell you about it in words before you try to read the definition. It's going to be a really big graph. So basically, there's going to be a vertex for every state of the game. So remember, what is a state of the game? It is a choice of actions for each of the n players. So if there's k actions per player and n players, there's k to the n game state. So there's a lot of them. Okay, but that's okay. Like, that would be annoying if we were coding up an algorithm, but when we're just like conjuring the object in a proof, it's no big deal. Okay, so let's imagine a game. It's got a whole lot of game states, exponentially many game states. But like, nevertheless, I can imagine a giant graph that has one vertex for every game state. Okay. So those are the vertices of the graph. Now, let's think about the edges of the graph. Basically, I want there to be an edge between vertices, right? An edge between two game states, a directed edge from game state A1 to game state A2. If there is a way to get from the first game state to the second game state via one step of best response dynamics. Okay, so let's think about what that means. Well, first of all, like in one step of best response dynamics, like definitionally only one player is changing their action. It's like for sure, if there's an edge between, like game state A and game state B, it had better be that A and B are actually identical except in one coordinate. They must be exactly the same except in one player's action. Okay, so like most vertices can't have edges between them just because of that, because they differ in two or more players' actions, right? If two game states that differ in two or more players' actions cannot have edges between each other in this graph we're constructing, but if they differ in the unilateral change in one player's action, they might. Okay, and not just that, right? Like, I need that the action that these two game states differ in actually constitutes a better response for the player changing their action. So it's got to be that if there's an edge between A and B, it's got to be that the cost for the player that is changing their action between A and B, the player whose index I is the one index that differs between these game states, actually decreases. It's actually smaller in game state B than game state A. Okay. So does that make sense? So I'm like defining some very big graph, but like hopefully it's got some kind of intuitive structure. Like there are edges every edge in this graph corresponds to what could potentially be one round of best response dynamics. If you started at the beginning of the edge, there would be some player who could unilaterally change their action to get you to the end of the edge, and in doing so would decrease their cost. And for every such pair, there is an edge. So the edges in this graph exactly correspond to sort of traversals that you could make in the state space of the game, corresponding to a single round of best response dynamics. Does that make sense? Is it clear what the graph is? Okay. So once we've defined this graph, we can think of best response dynamics as a traversal of this graph, right? Like we start somewhere. Best response dynamics starts at, doesn't care what game state we start at. So we could start at any vertex, any game state. And we move along by following edges in the graph. There might be choices, right? There might be vertices for which more than one player has a better response. So there's multiple outgoing choices. Better response dynamics could take any of them. Okay, so right, like the out degree could be as large as n. Any of the players could potentially have a better response move. But like better response dynamics, like although it's not fully specified, we don't know what vertex it starts at. We don't know what choices it'll make. like if I think about visualizing the trajectory of the game as we play better response dynamics, it would be some traversal of this graph. It would, there'd be like a little, dot specifying where we are, and the dot would move along the graph, always following one of the outgoing edges. Is that clear? Okay, so best response dynamics corresponds to some traversal of this graph. What are the Nash equilibria in this graph? What do the Nash equilibria look like? Yeah, they're sinks, right? So like a Nash equilibrium, a pure strategy Nash equilibrium is a game state such that nobody has a best, such that everyone's already playing a best response. So nobody can unilaterally deviate to improve their cost. And so if we're at a Nash equilibrium, there must be no outgoing edges, right? Because outgoing edges indicate that someone can change their action and decrease their cost. Similarly, if there are no outgoing edges, by definition, we're at a Nash equilibrium. Okay, so best response dynamics corresponds to a traversal of this graph. Nash equilibria are the sinks in this graph. What does it mean that best response dynamics converges? If you tell me best response dynamics converges, what do I know about this graph? There are sinks. What else? No cycles. Well, sinks, you could have a graph that has sinks and also cycles, but like the meaning, like what we mean when we say best response dynamics converges is that this graph has no cycles, right? Because we asked for all these universal quantifiers. No matter where you start, no matter what order in which you let players deviate, you always converge. Well, that wouldn't be true if there was a cycle in this graph, because in particular, if we start somewhere that leads into the cycle and we consider the sequence of best responses corresponding to the cycle, we might continue traversing the cycle forever and never reach a Nash equilibrium. Okay, so the Nash equilibria are sinks in this graph, and the hypothesis of the theorem that best response dynamics converges, or the hypothesis of this direction of the theorem, can be translated into the language of this graph as meaning exactly the graph is acyclic. There are no cycles in the graph. Okay, makes sense. Okay, so what we need to do, right? You gave me a game, which I can sort of unroll into this graph. You told me the game is such that best response converges, so I know that the graph is acyclic. I need to somehow use this graph and the fact that it's acyclic to construct an ordinal potential function for you. Okay, that's like what we need to do. Okay, so starting with some basic facts. I need to use somehow that the game is acyclic, right? That the graph is acyclic. That's like an important hypothesis here. So like, I claim that one simple implication of the fact that the graph is acyclic is that from every starting point, from every vertex in this graph, there is some sink that is reachable through a path through the graph. Can anyone tell me why? You're shaking your head.
Like a cycle that then had like an outgoing branch as well. Like if you had if you take 3 points per connected in a cycle, but then also pointed to a sink like outside of them, would that?
What then?
I guess you're saying that is.
So something like that would sort of correspond to a scenario where there exists a sequence of better response moves that reaches a Nash equilibrium, but not every sequence does. In particular, there's a sequence that goes around the cycle. So like a game that had that property, we would not say that best response dynamics converges. When we say best response dynamics converges, we mean for every possible sequence of better response moves. So in particular, there aren't, like it rules out this case. There are no cycles. Okay, but
Never mind, I read the.
yeah, but say there are no, like, yeah, the starting premise is there's no cycles in the graph. How come I know that from every starting point I can reach a sink? Yeah.
the best response. Otherwise, we didn't, but then that node would be.
Yeah, although I guess this is just like a fact about graphs. So like you don't necessarily need to think about how we constructed the edges. Like I claim in every acyclic graph, there's a sink that is reachable from every state. Yeah.
Oh, wait, are we saying like if it's acyclic, then show that
Not only that there's a sink, but that there's a sink that is reachable from every vertex.
show there's a sink, it's just think of maximal path, right? Then that the ending vertex has to be.
Yeah, and I guess you can modify that to argue that that's true from every starting point as well.
Yeah. Just think of maximal path from each starting point.
Yeah, or maybe like even simpler, like just imagine that you're standing on one of these vertices and then you decide to take a walk and you're just, you're gonna like step along edges as you see them, unless you get stuck. And there's no cycles in the graph. So like, where are you gonna go on this walk? Like, it might be that you end up in the same place you were before, except that can't happen because that would be a cycle. Yeah, so like if you're taking this walk and you can't visit the same state twice, you can't because there's no cycles, then, like my walk can't have infinite length because the number of steps I take can't be more than the number of vertices in the graph. And so whatever path I end up taking, I have to end up at a sink because I will eventually reach a point at which I can no longer go on. And that'll in particular be a path from me to the sink. And so at every vertex, from every vertex, there is a reachable sink. So in particular, it makes sense to think about the length of the longest finite path from a vertex to a sink. Because I know from every vertex, there are reachable sinks. And I know that every path in the graph is finite because there's no cycles. Okay, so that's going to be my potential function. Let's make sure everyone's clear on what this is. Right, so what is it? First of all, what is a potential function? It is just like the kind of object it is. It's just a mapping from game states to numbers. It's a way of labeling the game states with numbers. And this is the way I'm choosing to do it. I am labeling every game state with the length of the longest path from that game state to any sink in the graph. Okay, I know there is at least one such path, and I know that the length of any such path is finite, and so this is like a well-defined function. Yeah. The number of steps. It's an unweighted graph, so just the number of edges I need to traverse along the path. Okay. Is the definition clear? Like this is some function mapping game states to numbers. And so like we need to argue it's a potential function. Now remember, an ordinal potential function. So remember, the edges in this graph correspond to better response moves. And an ordinal potential function must have the property that for every better response move, right, for every better response move, for every unilateral deviation that decreases the deviating player's cost, the potential must decrease. Now, all of the better response moves correspond to edges in this graph. So what we need to show is that for every edge in this graph going from A to B, the potential at B had better be lower than the potential at A. If we can show that, that will mean that our function is indeed an ordinal potential function. Okay, so I claim that this is true. I claim that in fact, not only is the potential at B lower than the potential at A, it is lower by at least one. The potential at A is at least one larger than the potential at B. Can anyone tell me why? Yes. Yeah, like phi of A is the length of the longest path from A to a sink. So you know, I'm trying to think of what is the longest path. Oh, question. Not necessarily. There could be multiple paths, right? There's potentially multiple outgoing edges, right? So I could have something that looks like this. Right, so this is, I claim the potential here is at least one more than the potential here, but not exactly one more because there's a even longer path. Say that again. Well, remember this is a directed graph. So, you know, there can be like the out degree is not just one. And if I took away the directions, there could be cycles. There's just no directed cycles. Okay, but right, so this isn't an equality, it's an inequality. But right, why is it the case that the potential at A has to be at least one more than the potential at B? Well, like what's the longest path from A to a sink? You know, who knows? But like if B has already done their homework, B knows the longest path from B to a sink, and I have an edge to B. One thing I could do is take one step to B and then take the longest path from B to a sink. That would be a path that is one longer than the longest path from B to a sink. Maybe I've got another one that's even longer, but my longest path is at least one more than B's longest path. So this is indeed an ordinal potential function, and therefore not only does the existence of an ordinal potential function imply the convergence of best response dynamics, but the convergence of best response dynamics implies the existence of an ordinal potential function. Okay, I'll see you guys on Thursday.
So, exciting, not to really